Thank you for the introduction. My name is Abdullah Bajwa. I'm a postdoc in engineering science. And today I'll talk about how the internal combustion engine, which is a machine which has been driving our cars for over a century now, how that can be used to support the decarbonization of the transport sector. Currently, around 14% of the world's greenhouse gas emissions come from the transport sector, which is a pretty significant contribution, and we need to change that. Around 44% of this 14% comes from what are known as light-duty vehicles. You can think of them as our private cars, our SUVs, so a pretty hefty share. And the second biggest contributor is road freight, which includes trucks. Railway, air, and sea also contribute significantly, but in lower shares. And we've been told by climate scientists that business as usual, where we continue burning fossil fuels the way we have, it cannot be sustainable. We would cross the ecological thresholds of our planet, and we need to reduce the CO2 emissions, the greenhouse gas emissions, which are being released from our transport systems if we want to meet the climate change mitigation targets set by climate scientists. There are multiple decarbonization options for different sectors of the transport. If we talk about the light-duty vehicle sector, our private cars and SUVs, electrification, which means replacing the internal combustion engine with electric machines and batteries, is fast becoming a very promising option. And that is because the life cycle greenhouse gas emissions from electric vehicles are significantly lower than those from internal combustion engine powered vehicles. Hybrid electric vehicles, which have an engine as well as an electric machine, fall somewhere in between. Hence, not surprisingly, there has been a very sharp uptake in electric vehicles, and it is projected, for example, shown over here for the UK market, that in the next decade or two, internal combustion engines would be replaced by battery electric vehicles. That's all good, and that's all relevant to our cars, and we can agree that electrification of cars is a good strategy to decarbonize the light-duty vehicle sector, and the infrastructure needed to support this transition from a fossil fuel-based automobility regime to an electric-based one is becoming mature fast, and it's becoming green as well. But if we move towards some of the more energy-demanding sectors of the transport system, for example, big trucks like these or ships, then electrification all of a sudden becomes a lot more challenging, because you need a lot more energy stored on board, and the weight of the batteries that you would need to provide that energy, that becomes untenable. Not only because it would make your vehicles very heavy, it would also impose a significant payload penalty. For example, if we talk about long-haul trucks, at present, according to one estimate, the price of an electric truck is almost 3 times as much as that of a comparable diesel truck. So while we wait for the price of electric trucks to become more affordable, I think the internal combustion engine can play a role in making sure that we get to the zero carbon goal that we have set in a responsible manner, where we release as little CO2 as we can while getting there. So for some of the more energy-dense sectors of the transport system, we might need a more diverse portfolio of propulsion technologies, which might include electrification, fuel cells, and the internal combustion engine. I'll use the next few slides to elaborate what exactly is the challenge with the internal combustion engine, because there's no denying the fact that the internal combustion engine, which has been powering our automotive fleet, releases a significant amount of greenhouse gases into the system. The way internal combustion engine works as we are all familiar is that we add fuel to it, and as a result, we get useful work or useful power out of it, which has historically been reported in the units of horsepower, hence the horse. But that's not the complete picture. When we add fuel, it undergoes combustion, releases its chemical energy, gives us useful work, but it also produces CO2, which is the most problematic greenhouse gas and responsible for global warming. In addition to that, there are also harmful pollutants produced when you combust a fuel in an engine. Some of the significant ones are oxides of nitrogen, carbon monoxide, soot particles, and unburned hydrocarbons. And these pollutants can significantly degrade the quality of the air that we breathe in and are responsible for many respiratory problems. But I'll contend at this point that the problem is not with the engine, which I'm trying to point to, it's with the fuel that we put in the engine. And to make that argument, I'll use the example of the fuel that we use currently, petrol or diesel. These fuels can be characterized as liquid because they exist in the liquid phase, hydrocarbon fuels. Hydrocarbon meaning that they're composed of hydrogen and carbon atoms. And it is this particular formulation of the fuel which is responsible for most of these unwanted emissions. The carbon reacts during combustion to produce CO2, CO, and unburned hydrocarbons. The fact that the fuel is a liquid is responsible for soot emissions that we see. And the NOx emissions, that's an artifact of high temperatures which are experienced during combustion in the engine. So now let's imagine a fuel which, instead of being liquid, is a gaseous fuel. And instead of being a hydrocarbon fuel, is a carbon-free fuel. Then, theoretically, we can get rid of four out of the 5 harmful emissions that are produced. If we don't have carbon, we won't have CO2, CO, and unburned hydrocarbons. If the fuel is not a liquid, we won't have soot emissions. We still have NOx emissions if the combustion temperatures are high, because NOx, oxides of nitrogen, they are produced during combustion at high temperatures. So, many of you might have guessed that the gaseous carbon-free fuel that I was alluding to is hydrogen, and because of its unique properties, which theoretically can rid us of many of the harmful emissions, it has seen a lot of interest in recent times, especially in the off-road, the off-highway transport sector, which includes excavators and trucks. There's even a UK-based company, JCB, which has launched the first commercial hydrogen engine in the world, and other big off-highway manufacturers are also investing heavily in it, because as we move to a carbon-free transport future, we for a multitude of reasons might need help from the internal combustion engine. But as mentioned previously, NOx is still a problem. But there are engineering options that we have to mitigate this problem as well. The first solution that we have is to use strategies and after-treatment systems which have been developed for conventional fuels, petrol and diesel. Because over time, the allowable level of NOx emissions from cars has been regulated down significantly. So there are technologies that exist for conventional engines which can be used for a hydrogen engine as well. Secondly, there is a unique property of hydrogen that it can burn with a lot more air as compared to liquid fuel. So it can be diluted with a lot more air, yet be able to form a sustainable combustion reaction where flame would extinguish. And the advantage of that is that if you mix a lot of air with the fuel, the air acts as a heat sink and the temperature of your combustion is low. If you run with significant dilution, or if you run significantly lean, then studies have shown that you can essentially remove all the NOx emissions from your tailpipe. A few other challenges that engineers are working on, and some of these we work on in our lab as well, are about how can you get enough energy into your engine, because hydrogen, being a gaseous fuel, carries less energy per unit volume per liter than a liquid fuel. Some of the ways which people are exploring are compressing hydrogen to very high pressures, even liquefying hydrogen, and are looking at novel designs of fuel injectors where you can inject hydrogen directly into the engine cylinder, and through that you can push more energy per unit volume. This is an optical study where people have seen how a jet of hydrogen ejected from a hydrogen injector, how it looks like, and how it mixes with the gases in the cylinder. Other carbon-free, carbon-neutral fuels which are being looked at by engineers out there include ammonia. Ammonia has garnered a lot of interest in the shipping sector. I won't go into that, but people are looking at that. And recently, so-called e-fuels, they've seen a lot of interest as well from some of the niche automotive manufacturers which need not a drop-in solution to make their existing automotive fleet carbon neutral. That's pretty much everything that I'll talk about today. And I'll conclude with the point that everything that we do as engineers, we focus on improving the technology, improving the propulsion systems. But if we need to meet our climate change mitigation targets, those improvement efforts would have to be complemented by shifting to other modes of transport. For example, non-motorized transport, driving less, cycling more, and avoiding the use of transport where it can be avoided. So it would have to be a collective effort. Thank you.